like I said, the absolute way to evaluate aerodynamic performance is your wind tunnel. So what is wind tunnel? It's basically a large room, right? And there is a stream of air flowing at constant velocity, and the velocity of the air can be controlled very precisely. And you have your object, right? So this right here is your GCM truck. Okay, so this right here is your GCM truck. And what we are doing is we are just letting the air flow through the truck. And you can see that there are a lot of points here. So if I use a different color, maybe black, you can see that there are so many points. So these are what you call as pressure tabs. In other words, these are nothing but pressure sensors. They will basically record the pressure at that point at a given point in time. So they are really precise. And you have you have around 200 pressure sensors on the entire truck surface. So the advantage is once you have this pressure data, you basically have a pressure distribution, which basically says in which area you are having low pressure, right? So remember, usually in the front of the truck, you have high pressure, and usually in the back of the truck, you have low pressure. This difference in pressure is what is actually stopping the truck. That is the air resistance, correct? So the whole idea is to identify these low pressure areas and see if there is something that you can do to basically minimize the pressure loss. That is, at the end of the day, the job of an aerodynamics engineer in any company. It's easier said than being done, but that's the whole job of an aerodynamics engineer. Forget the full form of GCM. G stands for generic, C stands for conventional, M stands for model. Now, when you look at this truck, like, can anyone tell me what is weird about this truck? Does this truck look normal to you guys? What do you guys think? Why would someone do this? And why would someone put 200 or 300 pressure sensors? And these pressure sensors, just to go into a little bit more detail, so these are transient high frequency pressure sensors. They can basically measure pressure at a very high frequency, meaning you have excellent time resolution. So these pressure sensors are usually very costly. And this particular truck has around 200 of those pressure sensors. Why would you do it? It is scaled down to reduce cost. Well, if you have to reduce cost, I don't think cost is the issue, right? You're spending so much on pressure sensors alone. The cost of the truck is not a big deal. For testing big truck, we need huge wind tunnel. Yes, that's correct, but I'm saying the wind tunnel is just a one-time expense, right? And this is basically NASA's, this is a model that NASA built. So money is not an issue. Again, think of it like engineers, right? And these are the things that you guys need to understand. Like why, when people show you wind tunnel simulations, you know, it's cool and stuff. It's cool, that's correct. But why would they do that in the first place? More pressure sensors will require for bigger trucks? Not really. It's basically surface area coverage, right? That's not a big deal. It's a metal model. Okay, so Shivananda, so what? Well, okay. Let me just give a little bit more hint, or actually I'll give the answer right away. So the GCM initiative was done primarily for validating computational codes. And this slide basically helps you understand why CFD is a great option for aerodynamists. So when you run wind tunnel tests, right, these are very, very expensive, as many of you pointed out, right? And you know, there are softwares like ANSYS Fluent, Star CCM, Converge CFD. There are so many softwares. How can you trust the number that the computer is giving you? The short answer is you can't. Unless you have done the same problem before and you have done experiments on it, you can never be sure that your answers are right. Exactly, right? So you need to validate, and that is exactly why the GCM was built in a simpler way. So the objective behind the GCM program was to actually create very high quality experimental data on a model that is very simple to mesh and run CFD analysis on. So the reason why the model is so simplified is you can take this model into any CAD program or any meshing program, and the mesh generation process is going to be super easy. One thing that you don't see in this truck is that it basically does not have any underbody, right? Again, I cannot show you that. This is just a picture, but you have to kind of believe me. If I actually rotate the truck, maybe let me see if I have a picture. Actually, I don't. So basically, if you rotate the truck, you will see that there is no underbody. Why? Usually, if you have an underbody, that means you will need to use advanced cleanup tools to clean the model. And when you do that, you slightly deform the truck, right? And that because of that, your CFD results are going to change. So what people do is, what people did at NASA is they made the model so simple that pretty much any CFD solver out there would create almost an identical mesh. So if the mesh is identical, all the results boil down to what governing equations you're solving, what is the algorithm that you're using to solve, what type of turbulence modeling schemes you use, right? So you can basically do a validation study, and that is the first thing that everyone needs to do. You need to validate your CFD code, and then based upon the validation, you can figure out that, okay, if I'm able to validate an external flow problem at this Reynolds number, then for that same Reynolds number, if I modify the geometry, most likely I'm going to get the accurate answer, or most likely I'm going to get a very close answer. That is why this is being done.